Let's look at a thermal power station. So a thermal power station is that this is this internal energy, right? It's just heat energy. This is coming from burning something, right? So that's going to be energy that we get from burning some mass with some specific energy, right? Okay. This thing's going to have an overall efficiency. Efficiency is around 0.3 or 0.4, okay, or 30% or 40%, right? And the idea here is that we boil the water. It generates pressure. The pressure drives a turbine. So what we have, internal energy or thermal energy, turns into kinetic energy of the turbines, which turns into electrical energy. Okay, and this is the overall efficiency from this stage here, burning this stuff, to the electrical output. It's about 0.3 or 0.4. It's not terribly efficient. And that's because we waste a lot of energy condensing this. We waste energy here, we waste energy there, right? Anyway, so let's take a look at one of these. A coal-fired electrical generation plant has an overall efficiency of 34% and generates an average of 180 megawatts of electrical power. What quantity of coal with a specific energy of 47 megajoules per kilogram, because notice that coal is like this range, okay, would this plant use in 1 week? Okay, so a week is what? 7 days, 24 hours a day, 3,600 seconds per hour, right? Okay, so we're also going to use power is energy divided by time. So in this case, whoops, let's use a capital E, right? So in this case, our energy is power times time, and that's going to be our output, right? Okay, so let's figure out the energy output. That's going to be 180 megawatts, so times 10 to the 6th, and that's joules per second times the time. So it's going to run for a week. So 7 days per week times 24 hours per day times 3,600 seconds per hour. We are just like the king of units here, right? So seconds cancels seconds, days cancels days, hours cancels hours, and we end up with joules per week, which is exactly what we need, right? Okay, so 180 E6 times 7 times 24 times 3,600. And this is our total energy output, which is tremendous. It's 1.08864 times 10 to the 14th joules. But as tremendous as that is, the energy input is even more because it's not 100% efficient, right? It's 34% efficient, right? So efficiency is out divided by in, so therefore input is out divided by efficiency. So that's going to be, this is our output, right? 1.08864 times 10 to the 14th divided by the efficiency is 0.34. And that E just means times 10 to the, right? Okay, so I'm going to take that number, divide by 0.34. Okay, and I get that the actual energy input, okay, this is our input energy, is equal to, and this comes from burning the coal, okay? So 3.20188, etc., times 10 to the 14th. And this is the energy that comes from coal, right? So we know that the energy output is mass divided by, or times specific energy. So therefore, the mass is the energy divided by the specific energy. So it's going to be 3.20188 times 10 to the 14th joules. That's how much we need. Divided by, let's see, the energy is 47 megajoules per kilogram, right? So 47 times 10 to the 6th joules per kilogram. And notice that if you divide joules by joules per kilogram, you're going to end up with kilograms, right? So divide this by 47 E6, and I get a very unhelpful number. It's 6812515.8 645 joules. So let's put some commas in that. So 6.81 times 10 to the 6th kilograms. And at this point, we can't say, and this is sort of a sad thing, we can't say 6.81 megakilograms because, well, I mean, you could, but it would be weird, right? Because kilo is already a prefix. And that's the problem with having a prefixed unit as your base unit, right? I guess you could say 6.81 gigagrams if you wanted to. That'd be kind of fun. GG, big G, little g. But I don't think anybody does that. So anyway, there you have it. I think we just have to do this.